Today we're looking at hash algorithms for secure password and storage. In software development, we're taught that speed is the ultimate goal. But interestingly, when it comes to securing passwords, speed is actually a critical vulnerability. In this project, we compare legacy hashing methods against modern standards to demonstrate exactly why this is the case. The core conflict lies between fast hashes and memory hard hashes. Algorithms like MD5 and SHA were designed to be efficient, which unfortunately allows attackers to guess millions of passwords per second. In contrast, modern algorithms like Argon2 and Bcrypt are designed to be intentionally slow and resource-heavy in order to neutralize hardware-accelerated attacks. To test this, we simulate a data breach scenario where an attacker has already bypassed our network defense and has stolen all the hash passwords from our database. They are now performing an offline attack using their own hardware to crack the password hashes. Given this scenario, network rate limits don't exist. Only computational power matters, which means we're at the mercy of the hashing algorithm used. We built a script as a way to simulate this data breach brute force attack. This script will allow us to benchmark different algorithms and measure these computational costs. It's built in Python 3.8 and uses a standard hash-lib library for legacy algorithms like MD5. For modern algorithms, we use the integrated specialized libraries like Bcrypt and Argon2 CFFI. Our primary metric is the throughput, which measures how many guesses an attacker can attempt in a single second. The difference is visible directly in our code. For SHA-256, the implementation is done by simply appending a salt and hashing it. It's fast and lightweight. Whereas if we compare it to Argon2, where we don't just hash, but we also configure a specific hardness to the algorithm with an enforced memory cost of 64 megabytes and a parallelism of 2 threads. Doing this configuration forces the processor to fill RAM for every single guess, destroying the efficiency of an attacker's hardware. To run the tool, we should first create a new virtual environment. This virtual environment will contain the libraries required for this one project. Once that's done, we can activate it. Afterwards, we move on to installing the required dependencies via pip by using the library list present in the requirements.txt file. Once that is done, we can run the script with an argument to start the benchmark. This argument is the password we want to hash. Here's the output that we get from the script, where we can validate our theory. With MD5, our tool achieved nearly 2.3 million attempts per second. This means that an 8-character password could be cracked almost instantly. For SHA-256, we can see big differences between the salted and the unsalted versions, but we can also confirm that it is insufficient. While it slowed down the attack by roughly 4 times, it still allowed over 600,000 guesses per second, showing that salting, despite being effective at preventing rainbow table attacks, it doesn't prevent brute force attacks. However, with newer algorithms like Argon2, we can see that it dropped the throughput to just 25 hashes per second. This massive reduction in speed effectively makes brute force attacks computationally impossible. With this information, the results are clear. To stop a brute force attack, you must slow it down. Switching to a resource-intensive algorithm isn't just an option, but is a requirement for today's password security. The development of this tool was only possible by Python and the open source community, specifically the Bcrypt and Argon2 CFFI modules, which provide the necessary cryptographic functionality for our simulation. You can find the full source code on the GitHub URL on the screen. Thank you again for watching.